Scientific American Day. Can someone please play the national anthem of the USA somewhere?
Papa Flammy's random OIA.
Good morning, fellow mathematicians. Welcome back to another video. Not another video, another video. That's what I'm saying. My another has transformed a little bit into something fucking retarded over time. But welcome back to
Papa Flammy's random OIA.
Oh yeah, let's dive right in. So we are going to take a little geometry problem today, and I don't have much chalk left, so we have to make it short, my boys. No, I still have some chalk left. Never mind. So this was originally a little homework problem back in my elementary geometry class, and as a matter of fact, Papa bless, I was the only one solving it the way I'm going to present it to you today. And the boy doing the tutorial said, that's such a fucking great way, he's going to remember it in the future. So no one in my class had thought about solving this problem like this. That's why I'm going to present it to you guys today. So the quest for today is, well, imagine a little circle right here, perfect fucking circle with a center somewhere in the center and a radius of r. And this radius we want to be finite, obviously, otherwise it wouldn't be a circle, it would be a straight line. Never mind. So you are going to draw a little triangle into here, a triangle inscribed in the circle, corners touching the outer line, the arc of the circle, and well, what type of Euclidean triangle, for example, equilateral? Little spoiler alert, it's going to be the equilateral triangle, or isosceles triangle, blah blah blah, is the one with the largest area. That's our quest for today, and for this I would like to name the corners a little bit. So let's say we have P, Q and S, for example. I don't really care how you name them. And what we want to do at first, we would like to fix our side P and S or QS or whatsoever in place. So that's the first step of solving this thing right here. So at first let's fix PS. That's the line segment PS, and what would happen to our little drawing right here? Well, we would transform it like this. We now have the circle right here, and we have this side fixed in place. P, S and Q. Okay, coolio, but what else could we do? Well, we want to maximize, so that's a calculus problem basically. We want to maximize this area of this triangle right here. So how can we do that? Well, at first let's take a look at the area of a triangle basically. And I'm going to give you a quick little visual proof because people like visual stuff, I really don't know why. But let's consider one triangle, boy, like this right here, and let's place the exactly same triangle like this here. So that means the area of one triangle is just half the area of this whole thing right here. Now let's cut this thing up, put it here, and it's going to fit exactly in here. And now we have the height right here on our side A. This is the side A. And you see, this is also the side A, and we have a rectangle right here. So the area of this rectangle is nothing but the height on A times A. And if we want to get the area of our triangle, we just have to divide this whole thing by 2. So that's the area of a triangle. Now, we just have to put a little height into this thing right here. So we want to put a height on the side PS. As a matter of fact, if you construct a height on the side, that means that this height is perpendicular to our side PS in this case. Okay, cool, that's just a little fact. So that means our area of this triangle A is nothing but the height on PS times our side, the norm of this PS, over 2. So this thing is just the norm, that means the length of the side, if you don't know this notation. But the cool thing is, we have fixed our side PS, so the only way to maximize this area of this triangle is to play around with our height right here. So we want to maximize our height in order for us to maximize our area. Okay, here's another thing we want to do. How could we maximize our height right here? Well, what we could do, let's take a look at this triangle. This right here is the center of our circle. This is P, S and Q. And what we want to do to maximize our height, well, we want this height to run exactly through our center right here. And we have a circle right here. And that means that our height that runs from the outer arc to the side, well, exactly divides this side PS right here. You can do some vector analysis and you will find out that this height right here divides the side PS into two equal parts. And let's say we have some point R on this line right here. So that means we have a line segment, PR, being exactly equal to a line segment, RS. Okay, just a little matter of fact. And also what this implies is that this side QP and QS are equal, which also implies that this triangle right here at the moment is an isosceles triangle. Okay, cool. So we already came pretty far actually. But now we have a little problem. So we still want to maximize our height right here. How can we do that? Well, at the moment we only know that this side right here, QC, is nothing but our radius, because this point up here, Q, lies exactly on the circle and our center is the center point. So that means this right here is the radius, and we don't know anything about the side CR. Let's call it X, for example, and that's where our calculus problem comes in later on. Okay, I hope you can follow me on all of that. So that means our height right here, and this is still a right angle right here, our height on PS is nothing but R, the radius, plus X. Now what we still have left is our PS right here, and I want you guys to remember that the side PR has the same length as the side RS. That means if we add those two together, we exactly get our PS right here. So that also implies that our side PS is nothing but, let's say, 2 times the side PR. I hope you can see where this came from. Okay, and the cool thing is, if we know what PR is, we can also find out what X is right here. So we can, or let's say we can find out what our PS right here is. Let's put it that way. Because we can make a little right triangle in here. So, you know, P lies on the circle and C is the center, so that means this side is nothing but R, and we have our X right here. And by our Pythagorean theorem, we know that the side PR right here is nothing but the square root, positive square root. We are in the Euclidean space, so all side lengths are positive. R squared minus X squared. And you know, PR is nothing but 1/2 PS. So if we multiply, 2 times this stuff right here is nothing but our PS. Yeah, let's put it that way. Okay, cool. That's a lot of stuff we have to derive before getting into real calculations. So we now have an expression for our area right here, which is nothing but, and I hope you could follow me on everything I said. You can also do it differently by parameterizing the circle right here and then playing around with vector analysis stuff, but I want to do it that way because people like this pure geometry stuff. Okay, so what do we have? We have 1/2 times the side PS, which is nothing but 2 times R squared minus X squared. And also we have this height right here, which is nothing but R plus X. So you see, this is going to cancel out. And in order for us to maximize this area, which is now a function with respect to our X right here, we want to find the maximum of this thing right here. How can we do this? Well, differentiating this side this area with respect to X, and finding out what the maximum is. That means setting the first derivative equal to 0, and then we can differentiate it a second time and see if this value for X that we found out is less than 0, right, for it to be maximum. That was a pretty slow start, and we are going to just dive through everything now. So, like I said, we want to find out the first derivative of this thing right here with respect to X. So let's do this. So dA of X differentiated with respect to X. Well, I have rewritten this expression right here equivalently with the 1/2 power because that's easier to comprehend for most people. So we also have ddx of this stuff. Obviously we need to use the product rule, and I would like to start with differentiating this part right here on the right, where you see the differential of this thing is just 1, so we end up with r squared minus x squared to the 1/2 power, or the square root of that thing. Now we want this part to stay, so positive r plus x, and we would like to differentiate this part. So at first drag the power down and reduce it by 1, so we have 1/2 r squared negative x squared to the negative 1/2 power, and also we need to take the inner derivative of this thing. That's just a constant, so we end up with negative 2 times x. And you see this 2 and this 1/2 is going to cancel out, and I'm going to rewrite this a little bit. So we have square root r squared negative x squared, negative sign to the front, negative x r plus x over r squared minus x squared, and the square root of that whole thing. Let's put it that way, not with the 1/2 power. Okay, so that's actually what we get. And well, the cool thing is we can advance this fraction right here, or this term, by a fraction, just square root blah 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 over square root blah blah blah. So we can do this, so we end up with, so square root of this thing times this is just square root squared, is just the argument itself, so r squared negative x squared, and then we can bring those fractions together in the end, so x times r plus x squared, negative x squared, sorry, this way, over square root r squared negative x squared. Okay, coolio, and we can bring those negative x squares together to 2x squared, negative 2x squared. And like I said, we want this to be equal to 0 in the process. There's only really one way for our fraction right here to be equal to 0. Well, the first case would be when x goes to infinity, because that would be 1 over infinity, and that would just be 0, you could say. But our x is strictly less than our r right here, so it was just a small portion, a small line segment in the circle. So that means since our radius is finite, our x is also finite, so it can tend to infinity. We got that out of the way, so that equivalently means that our numerator must be equal to 0. That's what we can conclude. So r squared negative 2x squared negative x times r must be equal to 0. Now we can multiply both sides by negative 1/2, you could say, to get rid of this 2 in front right here and this negative sign. So we end up with, and that's not equal to 0, x squared minus, this term next, let's do it that way. So positive r over 2 times x, and then negative r squared over 2 must be equal to 0, and you see now we can just use the quadratic formula on this one right here. That's something we can do. So we know that x, 1 and 2 is nothing but, so negative this stuff right here, so negative r over 4, positive or negative square root of, and now we have negative r squared over 16, positive, because it's squared, and then negative and negative becomes positive, so r squared over 2. And you see we can advance this fraction by 8 over 8 to get a 16 down here, and this is going to evaluate to 9r squared over 16. Taking the square root of that thing is just 3r over 4. So that means x1 is nothing but negative r over 4, positive 3r over 4, and the next value, x2, is nothing but negative r over 4, negative 3r over 4. And might be quite obvious, if we bring this together on x2, we end up with negative r. So that means x would be a negative line segment, so with negative length. That wouldn't really work, so this thing right here is basically a contradiction. We can't really use this solution in the Euclidean space. That also means that we just have to deal with this right here. And well, subtracting this right here, we end up with 2r over 4. That makes it r over 2. So we know that our x1 is nothing but half the radius. And like I said, we want to differentiate this a second time and see if this value right here corresponds to a maximum. And I'm going to do this in a little outtake. So, I think we have shown that this thing indeed corresponds to a maximum. I'm not really certain. Just take a look into the outtakes. So, I've gathered all the information once again on this sweet creamboard, blackboard, chalkboard, whatsoever. And you see, now we have found out what our x value is that we actually needed. So we also know what our height would be right here. So we can just plug this in and corresponding to 3r over 2 in this case. And we can also compute our side length, ps, right here. So that means ps would be nothing but 2 times square root. And now we have r squared minus r squared over 4. So we can just advance this fraction right here by 4 over 4, this r squared term. So we end up with 2 times the square root of 3r squared over 4, which is nothing but, well, this 2 and this 1 over square root of 4 is going to cancel out. So we end up with square root of 3 times r. Yeah, exactly. So that's our side length, actually. And we still have to find out our h, because we would like to compute our side lengths pq and qs. So, like I said, this is 3r over 2. And the good thing is, we are dealing with right triangles right here. And we also know what PR is, or RS. This is nothing but, 1/2 times PS. So let's put it here once again. So our side length PR is nothing but square root of 3r over 2. And now we can just use Papa Pythagoras right here. Like you can see, I have to think heavily about all of this, because once again I'm doing this all improvised. Yeah, just like with every video. So let's use Papa Pythagoras. So we want to find out our side length PQ now. So what is PQ? Well, PQ is nothing but square root, the positive one, because Euclidean space, blah, 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 of our h on PS, our height on PS, squared, plus our PR squared. So what is this going to correspond to? Well, this is square root of 9r squared over 4. And what is this? Positive. Okay, so we have something over 4, and then we have square root of 3, but squared is just 3, and r squared. Okay, coolio. And this is nothing but 12, square root 12r squared over 4. That's going to evaluate to square root of 3r squared. And this is nothing but square root of 3 times r. And I tell you what, we are already done, because at the beginning we have found out that this triangle we had here, after fixing our height, you can say, in place, and our PS, this triangle was nothing but an isosceles triangle, making PQ and QS equal. So we also know that square root of 3 times r is nothing but the length of QS. And you see, our square root of 3 times r was also our side PS right here that we had. So making this side, and this side equal, well, and if all side lengths in a triangle are equal, that makes it an equilateral triangle. That's really a hard word to say, I don't know why. And then we are done. So we have shown that if you inscribe a triangle in a circle, the type of Euclidean triangle with the biggest area is just an equilateral triangle. There we go. I hope you did enjoy this video. If you did, please like and subscribe, and please share those videos everywhere. That's a lot of effort this week, as with all those random integral blah 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 weeks. If you want to support the channel a bit more, buy those stupid ass t-shirts I created, or support the channel on Patreon. And up until the next video, let's continue this spiel. Oh, what is that? That looks fucking dope. Scientific American Day. Can someone please play the national anthem of the USA somewhere? No, I don't think so. A matter of time. Time's mysterious physics. Building time machines. The mind in time. ultimate clocks. Have a flammable day. See ya.